Alright, welcome back. We're doing the third homework in Thermodynamics II at South Dakota School of Mines and Technology. This is problem number 3. The homework 3 is associated with partial molar properties, both analytical and graphical. This is the last analytical problem. Okay, so I'm given this really god-awful equation. Let's write it out. So it says little g is equal to A. It says everything in A's and B's and C's. I hate A's, B's, and C's. I'd rather do 1s and 2s and 3s. So that's how I'm going to do it. So AX1 plus BX2 plus CX3 plus RT X1 natural log of X1 plus X2 natural log of X2 plus X3 natural log of X3 plus dx1 x2 x3. Yes, okay. And so, okay, so I have that. Come up with an expression for delta G mix and mu of A, or mu of 1. Okay. Based on that, what do you think A, B, C, and D represent? Okay. So, I mean, that's a secondary question. You know, we'll get to the answer, okay? But delta G mix, let's think about that one first. And so delta G mix, it asks, you know, I got to remember the definition. So delta G mix is just, you know, what is the difference between the G and the G as if it was an ideal solution. Okay. And I have to remember what's an ideal solution. Well, it's as if everything added together additively. Like, I mean, there's no mixing terms. It's just like, okay, I have 60% of this thing and I have 40% of this thing. We'll add those together, so to speak. Okay? So otherwise, you know, that math is G minus summation of xi G of I. Okay? And what is G of I? That is the Gibbs free energy of component I as a pure system. As a pure system. As a pure system. All right. Well, I have G, boy, which is that god-awful mess. And then I need G of I. Well, okay. So, what is G of I? It's the Gibbs free energy of component I as a pure system. Meaning that G goes to G of 1 as x1 goes to 1. Now, if x1 is 1, well, what can x2 equal? Can it equal 0.5? Can it equal 0.2? No. Can it equal 1? Okay. Can it equal x2? Well, yeah, but x2 only has one value if x1 is equal to 1. And what is the value of x2? That's right, it's equal to 0. And guess what x3 is? That's also 0. All right. And so, this one is equal to, okay, so A times 1 plus B times 0 plus C times 0 plus RT times this, well, let's put it on the next line. Okay, so plus RT, I've got 1 times natural log of 1 plus 0 times natural log of 0 plus 0 times natural log of 0 plus D times 1 times 0 times 0. Okay. Yikes. Well, that goes to 0, that goes to 0, that goes to 0. Okay, natural log of 0 is what? You know, I mean, if I think about, you know, this, okay, you know, it's this goofy thing here. But it's either minus infinity or infinity, okay? But what is 0 times anything? That's right, 0. So what is 0 times minus infinity? 0. What's 0 times positive infinity? It's 0. So what do you think this thing is? 0. Okay. What is the natural log of 1? That's right, 0. And anything times 0, again, even if it's 1 or not, is also 0. So all those things go to 0, okay? And all I'm left with is A. That's what I get. And I'm not going to do it, but if I repeat the same exact process, I'm going to get that G2 is equal to B. And I'm going to get G3 is equal to C. So I can even look at that question, that second part, right now. It says, based on that, what do you think A, B, C, and, well, we don't know what D is yet, but we know what A, B, and C are. A is how much Gibbs free energy is there. That's the Gibbs free energy of component 1 as a pure system. G2 is the Gibbs free energy of component 2 as a, B is the Gibbs free energy of component 2 as a pure system. C is the Gibbs free energy of component 3 as a pure system. So that's what they are. Those are the like pure system. I mean, that's how much I'm adding to my thing. And I can just eyeball that and be like, hey, that looks like an ideal solution. That's exactly what it's going to be. Okay. And we'll get into that. But yeah, I mean, when I look at that, that's the ideal solution thing. Okay. But you know, let's do the math. Let's plug it into here. But it's xi but times gi. So all of those things are going to go away, and I'm going to just have that left. Okay. And so yeah, essentially when I plug this in, you know, my delta G mix is going to equal RT times the summation of xi natural log of xi plus dx1, x2, x3. Okay. So what's D in this context? Well, that's my mixing term. That's how much I'm adding things to mixing. You might be like, well, what's this thing? If this is the mixing term, what's this? Well, we'll get into that. But as an illusion, A-L-L-usion, this is the entropy of mixing, and this is the enthalpy of mixing. But we'll get into that. But basically, I mean, you don't have to know that this is the enthalpy of mixing. Just know that D is a mixing term, okay? But we'll learn that this is the entropy of mixing right there. So, in any case. It also asks for mu1. Well, what's mu? Well, mu is chemical potential. But what does that have to do with partial molar properties? Well, let's go back to the definition. Let's go back to our notes. And it said that mu, component 1, was equal to, yeah, it was D capital G, D N 1, and there was one of those here. It was constant, constant canonical variables, and the canonical variables of G were T, P, and okay, all the other moles. Okay, so N, J, and I equal to 1. Well, what does that look like? Well, that looks like partial molar G1 if you ask me. That's what it is. So really, I'm asking you, what's partial molar G1? Okay. So this is a partial molar property. That's step 1, and then okay. Now, is this binary? No, it's not. Now, I regret not giving you a mathematical binary problem, so, you know, there's no binary examples on this problem. Not analytical, but, you know, like I said, sometimes it's easier, sometimes it's not, okay? But essentially the steps are the same, okay? So, so G, okay, do I have a capital G? Nope, I have a little g. How do I get from a little g to a big G? You know, for funsies, let's just treat this as a two-component problem. Does that mean I should go the binary route? No. The reason why is because those natural logs make this a beast. Okay, so let's just avoid that. Okay, but I'm going to get a very similar trend Well, okay, I'll do all three. All right. Okay, so G is equal to, so I multiply by NT, and what I want to see is you multiplying by NT, but then do it correctly. Okay, so that's the two parts to that. So in terms of AX1 times NT is AN1 plus BN2 plus CN3 plus RT times this nonsense. Now, in terms of x1 natural log of x1, is that n1 natural log of n1? I cannot distribute the n total to what's in the natural log. So technically it's n1 times natural log of x1. But I don't want to keep anything in x's, okay? Because I don't want to be confused about x being constant, because is x constant? If I change the moles of component 1, does the mole fraction change? Let me read that a different way. I have air. I remove oxygen molecules. Did I just change the mole fraction of oxygen in the air? Yeah, dang right I did. Okay, so I do not want to assume it's constant, so I want to write this like this. Okay. Now the other ones, and I'll get the same thing. So n2 natural log of n2 over nt. Plus n3 natural log of n3 over nt, and then plus d. Now, it says x1, x2, x3. Does that mean it's n1, n2, n3? Well, before I answer that question, what do I always need to keep in mind? I always need to keep in mind my units should be kosher, okay? So, I mean, ignoring what the units of A's and B's and C's and D's and whatever are, let's just assume that those units are consistent, okay? And so, x1, what's the units of x1? It's unitless, okay. And so when I went from an x1 to n1, my units became what? They became moles. Moles, 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 moles. Unitless because, well, that's unitless. So should I have n1, n2, n3? Is that moles? No, that's moles cubed. Okay. If you're unsure, some people, and I don't mind if you do this, some people will take their original G equation, so like, G equals, I'm not going to do the whole thing, but before they multiply by n total, they'll do this. They'll replace all of their x's with moles, and then, cancel out their n totals, and you'll realize, oh, well, I can cancel out 2 of them, but not all 3. I can cancel out 1, leaving 2, but not all 3. Okay, so this is my n, this is my G total, okay, and now I can do my derivative as normal, which is just another kind of beast in itself. Okay, so D, capital G, D, and, well, I'm not going to write that, I'm just going to write mu. Okay. Now, don't just skip to mu or whatever. I want to see this. I want you to recognize that partial molar property is related. Okay. So I want to see all of this, and not just like dg, okay? I want you to recognize that dg dni is the partial molar property. Now, I'm not just taking derivative because, oh, well, Dr. Hadley always took derivative. Okay, so I've got mu I, but I've already got my definition, so it's okay to just get down to mu I and start doing math. Okay, so a and 1. What is the derivative of a and 1 with respect to n1? That's it. All right, what about b and 2? Well, should that be, okay, n2, should I convert that to 1 minus n3 minus n4 or n1? No! If I take away the oxygen in this room, do I change the amount of moles of nitrogen? No! So that's constant, according to this. So, what's the derivative of a constant? 0 plus 0 plus RT, and this big god-awful nonsense. Okay, now, let's tackle the D. Okay. Let's do the D first. Okay. So, so is D a function of n1? No, it's constant. Is n1 a function of n1? Well, I would hope so. Is n2 a function of n1? Nope, it's independent, so that's constant. n3, constant. n total. Yep, you're right. It is dependent upon n1. So what I have there, do I have a quotient rule? No. I have a product rule. There's some chain rule in there too. Okay. So let's do the product rule aspect of it first. So let's just assume all of this is constant except for the n1. So what's dn1, dn1? Yeah, that's right, it's 1. So plus dn2 n3 over n total squared. Okay. Plus dn1 n2 n3 times derivative of 1 over nt squared dn1. Constant tp. But I can shorthand it that way in this case. I'm okay with that. You've already told me that it's constant tp. I'll assume that that's consistent. Okay. So I can just skip to the, I'm assuming you can do the math. And if you can do that math in your head, I'm okay with that. But some people need a little bit of a step. So we can do a funky function, or we can just write out the chain rule, or whatever. Okay, so let's just write it out as if it was a chain rule and say that, okay, f is equal to 1 over nt squared, okay, df, and that nt is equal to n1 plus n2 plus n3, so dn total, dn1 is equal to 1, okay, df, dn total is equal to minus 1 over nt, minus 1 over nt. Oh, no, that doesn't seem right. Minus 1/3. Yeah, minus 1/3 nt cubed times minus 3. And that goes down. That doesn't seem right. Oh, man. Been a long night. Yeah, that's the only thing that makes sense. Wow. N to the minus 2. Okay. So, I'm trying to do the integral. Okay. So that's minus 2 times nt to the minus 3, which is equal to minus 2 over n2 cubed. Okay. Now I feel better. Okay, and then df nt times dnt dn1 is equal to df dn1, which is equal to, well, 1 times that is minus 2 over nt cubed, and so I plug that into, well, I guess this thing right here. Okay. So, minus 2 over nt cubed. Okay. So there's that. And if you want to just skip to that, that's fine. I don't mind you doing that as long as you do it correctly. Okay. So I mean, if you just go from here to here, I'll know that you did the math correctly. Okay. Now a quick check. Did I do the math correctly? Well, all my moles should cancel out, and I should get x's back. So I have 2 down here, I have 2 up here, I have 3 down here, and I have 3 up there. Okay, well, that's good. Okay, now, what do I do about this god-awful mess? Okay, well, before we take the derivative, let's break that up in terms of log rules, okay? And so, just, as a side note, I got n1 natural log of n1, plus n2 natural log of n2, plus n3 natural log of n3, minus n1 natural log of nt, minus n2 natural log of nt, minus n3 natural log of nt. They all have natural log of nt's, so I have minus natural log of nt times n1 plus n2 plus n3. And what is n1 plus n2 plus n3? Yeah, so this all equals minus nt natural log of nt. So, and now I can take derivatives. Okay. So n1 natural log of n1, I got a product rule, so I need to do that accordingly. So, what's dn1, dn1? 1, so natural log of n1, plus n1 times the derivative of natural log of n1 with respect to n1. Well, that's 1 over n1. So 1 over n1 times n1 is what? Let's just write that like that, and it'll make more sense. Okay, we'll leave that. Okay, so n2 is n2 a function of n1? No, it's not. What about natural log of n2? That's also not. So that's equal to 0 in terms of derivative. So plus 0, just like before. And then I have the same kind of thing here that I kind of have to do up here. So I have, dnt dn1 times blah, blah, blah. Okay, so in this case, it's minus natural log of nt. Okay, so minus log of the natural nt minus, because it's the product rule, nt. Well, derivative of this with respect to nt is 1 over nt times dnt dn1, which is 1. So I have all that. Okay. All right. And I can combine my log terms now. And so this becomes, so that's 1 right there. And that's 1. And what's 1 minus 1? That's right, 0. Okay, and what's the natural log? And if I apply natural log rules, I got natural log of n1 over n2. Nt. What's that n1 over nt? That's right. Natural log of x1. Okay. All that nonsense to get down to natural log of x1. And that's just how it's going to work. Okay. Yikes, though. That was a chore. Okay. Let's see here. Well, that's what that was. So I got this, plus natural log of n1 over nt. Okay, from all that nonsense. Okay. And so let's just say that, before I go into the x's of that thing, okay. And so I've done my derivative, and now my next step is to convert all my n's to x's. Now, do I just convert them willy-nilly? No, I gotta make sure that everything does convert to an x, and I look at it, and yes, there is an nt for every n1. Okay, and so mu1 is equal to a plus d x2 x3 minus 2d x1 x2 x3 plus natural log of x1. I could combine, I'm going to, and now I gotta clean it up, okay? And there's really not much I can do, but a little bit I can do. So I still have a, I can combine my dx2 x3 terms. So dx2 x3, 1 minus 2 x1, okay? And 1 minus 2 x1 is not, because sometimes I can be like, okay, a lot of times I can be like, okay, 1 minus x1 minus x1. Okay, 1 minus x1 is x2, right? 1 minus x1 is not x2 in this case because there's 3 components. It's x2 plus x3. Okay, so really this becomes either 1 minus 2x1, which is probably cleaner than x2 plus x3 minus x1. Okay, so because it's 3 components, I really can't clean that up anymore, and so I'm done. Okay. But again, it asks for what does D mean? Well, there's my mixing term. Okay, that's again my mixing term. All right.